So now we discuss the second example problem for breadth-first search. So this problem is also from Kattis. It's called Rings. So this is a problem from ICPC East Central North America or ECNA regional in 2015. So ECNA is the regional that Purdue University competes in. So for this problem, we are given a cross-section of a tree in a two-dimensional grid. So looking at this picture here, it's the left side, it's the input, is essentially giving us this cross-section of the tree. So the interior are represented using this gray color, and then the outside are white. So the question asks us to assign a ring number to each of the cells in the tree trunk. So for example, the outmost layer are assigned 1. So essentially a particular cell is part of the outmost layer if it's either adjacent to a white cell or if it's adjacent to or it's on the border. So in other words, if it's adjacent to something that's outside the border. So in fact, I remember my first version of the code had the bug that I only consider adjacent to white cell as the border, and that will not correctly handle for example these two cells, because they're actually not adjacent to any white cells, but they are part of the border. They should be assigned 1. So after we assign 1, then any cell that's adjacent to a node that is assigned 1 will be assigned 2. And here adjacency consider only the 4-way adjacency, so up, down, left, right. So it doesn't consider diagonal adjacency. And the constraint is the number of rows and columns are both less than or equal to 100. So that means so this is one of the easiest problems in this problem set. So the parameter is not very large. So in fact, the problem can be solved in time linear in the size of the grid. So it can be solved even when the number of rows and columns goes up to I would say something like 5,000. It's solvable, or maybe at least 2,000 would be pretty safe. Okay, so you can stop the video now and think about how you would solve this problem. So the question, the problem essentially asks us to compute the minimum distance of each cell to the border. So it's a little bit similar to the previous problem where we want to compute the minimum distance of each cell starting from the top left cell. But here there is a difference, because we're not computing distance to any single cell, but rather to all the white cells and the border cells. So if you are directly adjacent to one of the white cells or the something outside, then your distance is 1. So that's the distance we are computing. And the way we solve it is we start by computing the outermost layer, which consists of all the cells that are adjacent either to a white cell or a cell outside the region. So basically, it itself is on the border. So we will do BFS. We will use a queue, which is initialized to include the outermost cells, and then we will process all the nodes in the queue, take a node out, take a cell out, and then look at which cell are adjacent to it and has not been visited, and then we will compute its distance and add it to the queue. So when we do BFS, in addition to the queue, we also need another data structure that maintains a state, and it's important to have the invariance that anytime we add a node to the queue, we also update the state to maintain the invariance. So here we use a 2D array, and which essentially is the input. We are using the same array both to store the input and also to store the final result. In order to do that, because the final result will have each of the cells labeled 1, 2, 3, and so we label the Y cell 0, and we label the initial values for the trunk cells using using a special value. So typically it's either -1 or integer dot max value. So either will work. So my code here use -1. So this is a Java code. I did not include the code for reading data to initialize this 2D array into either 0 or -1 based on the input data. So this is the code on this slide are for finding out the outermost border. So all the cells that should have a value 1. So we start by creating a deck, and then we scan through all the cells. And for any cell that is a part of a trunk cell, we will look at its 4 neighbors. So this loop through all the 4 possible directions to move, and then we compute the the neighboring cells index. And if the neighboring cell is outside the box, so then that means the cell ij is actually on the border. Then this will be considered, this cell will consider to have distance 1. The other condition that the cell will be considered distance 1, that is belonging to the outermost layer of the trunk, is when one of its neighbors is a non-tree trunk cell. So here, when its neighbor cell is marked at 0, that means it's outside the tree. So then any cell adjacent to it is considered a distance 1, the outermost layer, layer 1. So for each of those nodes, we add it to the queue, add the index to the queue. So this will loop over every cell that is a tree trunk, and for each of those we'll look at it 4 neighbors. So overall this is linear in the total number of cells, linear in R times C. So this slide gives the BFS code for assigning the ring numbers to all other cells. So I did not include the cell for printing the output, because this problem, they have a very specific requirement for printing output, so that you need some non-trivial code to do that. But it's non-trivial, but it's relatively straightforward. So this is the BFS code. We loop until the queue is empty. So we remove from the head of the queue, and then for each of those 4 neighbors, we check whether that neighbor is still inside the area. So we check that, and if it is, then we check whether this cell has not been, it's a tree trunk cell that has not been assigned a ring number yet. So we check whether it equals -1. So this is the tree trunk cell initialized 2. So in that case, if that is the case, then that means we have seen a new tree trunk cell that has not been assigned a ring number yet. So in that case, we assign the ring number to be the current cell's ring number +1, and we also add this to the queue. So these 2 lines, updating the state and adding to the queue, as I mentioned earlier for the previous problem, they always go together. So if you don't, then it's very likely that you may have a bug that you have to debug. So I also use a variable max ring just to remember the maximum number of the maximum ring number. This is needed to generate output because if it's a single digit, we print it the one way. If it's a double digit, we print it another way. So I need that information.